Today we're going to continue with our chapter on the mole, and we're going to focus a little bit more on converting quantities. Yesterday we looked at very simple conversions from moles to atoms, atoms to moles, moles to mass, mass to moles, and also atoms to mass as you saw in the do now, but we were always dealing with elements on the periodic table. Today we're going to be doing the same types of conversions, but we're going to be doing it with compounds, both ionic and covalent. Very similar, one additional twist. I think you'll be very successful with it. We'll get into percent comp later in the week with a really cool lab on percent comp and empirical and molecular formula determination next week. So what we want to do today is we want to relate the mole concept that we talked about yesterday to chemical formulas. We know that a chemical formula will tell us which elements are in a compound and the ratio or number of each element in the compound. So for example, we know for ionic compounds such as calcium bromide, again, metal, non-metal. In ionic compound, you'll have one calcium ion to 2 bromide ions. So for an ionic compound, you get the simplest whole number ratio of ions. For a covalent compound, such as carbon dioxide, you truly have 1 carbon and 2 oxygen in each molecule of CO2. So in a covalent compound, the subscripts indicate the true number of elements that comprise that compound. And what we're going to do is we're going to determine either the formula mass of an ionic compound or the molecular mass of a covalent compound. And this is very, very simple, and you'll be very successful with it. With ionic compounds, remember they're formed through the transfer of electrons. The metal loses, the nonmetal gains. You have a metallic cation and a nonmetallic anion. A formula unit of an ionic compound is the simplest whole number ratio of cations to anions. And again, you'll remember from our chapter on ionic compounds that the subscripts indicate the simplest whole number ratio of ions. And that's why we reduce when we write chemical formulas for ionic compounds. If you want to determine the formula mass for an ionic compound such as potassium bromide, you can do so very simply in grams per mole. We know how to get the molar mass of potassium off the periodic table. We know how to get the molar mass of bromine off the periodic table. So all we have to do is get both of them and add them together. So the molar mass of potassium off the periodic table is 39.098 grams per mole. The molar mass of bromine off the periodic table is 79.904 grams per mole. We talked about that the other day. And we have one of each, so we multiply each of these by 1, and then we simply add the two together. The formula mass for potassium bromide is 119.002 grams per mole. When you add these together, you're going to go to the simplest or the fewest number of decimal places. Same thing we talked about in adding and subtracting with sig figs. So this is the formula mass for potassium bromide. You can write it as an equivalency shown here, where you have 1 mole of potassium bromide is equal to 119.002 grams of potassium bromide. Very straightforward. Similarly, if we wanted to determine the formula mass of calcium chloride, the only thing more difficult about this one compared to the other one is that you want to make sure that you count the ions correctly. So in calcium chloride, shown here, you've got 1 calcium and 2 chlorine. So 1 calcium, 2 chlorine, hence the 1 and the 2. This is the molar mass of 1 calcium off the periodic table. This is the molar mass of 1 chlorine off the periodic table. To calculate the formula mass then, you have 1 times 40.08 plus 2 times 35.453 is 110.99 grams per mole. And you'll see the 2 decimal places here, and I maintain 2 decimal places here. You can write it as an equivalency as we did the other day. So something like this might be more similar to what you might be asked to do. And here I wrote the chemical formulas for you, but this is a super smart honors level class and you already know how to write chemical formulas, so that's something you'd be expected to do. And that's why I had said to you earlier when we were doing chapters 5 and 6 that you have to be able to formula write to be successful from here on in. So let's take a look at this example. We'll work it together and then you'll work one by your lonesome. It says calculate the formula mass of iron 2-phosphate in grams per mole. So the first thing we do is we formula write iron 2-phosphate, which you all should be able to do with ease. If you are still struggling with formula writing, you must go back and review classwork 2.1 and 2.2. Tons of problems on formula writing. Iron 2-phosphate. We want to determine the formula mass in grams per mole. We've got 3 iron, 2 phosphorus, and 2 times 4 is 8 oxygen. I got ahead of myself. So 2 times 4 is 8 O's. Be careful on that one. To get the formula mass, I've got 3 iron. On the periodic table, I look up the mass of iron and I find 55.847 grams per mole. I look at the periodic table for phosphorus, 30.974 grams per mole. Oxygen, 15.999 grams per mole. And in my calculator then, I'm going to plug in. Can you see that or no? Not really, right? Let me try and zoom out and bring this down a little bit because I think the light is so far from it that it's a problem. I think that's better. So we have 3 times 55.847 plus 2 times 30.974 plus 8 times 15.999 equals, and I have 357.481 grams per mole. And that is going to be the formula mass for iron 2 phosphate. Pretty straightforward, but you have to be able to write chemical formulas. Questions here? Pretty easy? Okay, try and do this one. It says calculate the formula mass of strontium chloride in grams per mole. Write the chemical formula and give it a shot. Should I reveal the answer or not quite yet? You ready? Yes? I got that. And I did get down to the 100th place because this was to the 100th place. That's not really a very big deal though. So the formula mass for strontium chloride. Now the first thing you look at is, did you formula write properly? You have to be able to formula write. If you are still struggling, please go over those classworks, redo them, come see me in the morning. You've got to be a master at formula writing. Otherwise, you're going to have big trouble. Alrighty? So that's formula mass. Formula mass is for an ionic compound because your basic building block, if you will, would be your formula units, your particles. You can also get molecular mass for a covalent compound. You do it essentially the same way. You're actually going to find it easier With a covalent compound, again, the subscripts indicate how many of each atom you really have, not a ratio. So shown here, we've got the molecular mass of carbon dioxide on the left and glucose on the right. And again, carbon dioxide would be 1C and 2 O's, shown here, atom together. For glucose, C6, you have 6 carbon. H12, you have 12 hydrogen. O6, you have 6 O's. And then you add all of this together. Molecular mass for a covalent compound for carbon dioxide is about 44 grams per mole, and for glucose about 180 grams per mole. Same basic concept. The ionic one is much more challenging, which you've also already been successful with. Now that you know how to determine molecular mass, that is the mass in grams for 1 mole of a covalent compound, or the formula mass, that is the mass in grams for 1 mole of an ionic compound, you can do basic conversions involving compounds. So this is exactly what we did yesterday, but instead of an element, you're going to have a compound. We're going to take a look at all of these examples together, and then you will have some practice problems to do in an effort to master this concept. In the first example, it says what mass of lithium phosphide, so that's what we're looking for, unknown, is equivalent to 2.45 moles of lithium phosphide. That's what's given. And again, if you can't formula right, you're going to have major issues. So start with the given. We have 2.45 moles of lithium phosphide. You have to be able to formula right, or you're going to have major issues. I'm having a few problems with this when I went to make it so you could read your calculator more easily. Can't seem to get, all right, so there we're at the bottom now. And now I can go a little bigger. Thanks, Irene. That should be better. And what we want to get to is the mass of lithium phosphide. And again, this is exactly what we did yesterday, except we have compounds instead of elements. So this will require that we get the formula mass and make an equivalency. So for lithium phosphide, how many lithium do we have?
3.
And how many phosphorus?
1.
Off the periodic table, 3 times the molar mass of lithium, 1 times the molar mass of phosphorus, again off the periodic table. And you're going to add those together. That's going to be the formula mass. The mass in grams of 1 mole of lithium phosphide. Now I've got moles of lithium phosphide here. So from my formula mass, I'll have 1 mole of it here. And we have 2.45 times 51.797 in 3 sig figs. That's 127 grams. And again, the only new piece is the formula mass piece. The setup is like we did yesterday. It's just a little more challenging to find that equivalency. Questions on number 1. Does it make sense? It's very easy for you to watch me do. I can't emphasize enough the importance of you doing. Let's set up the second problem. You talk me through. We're going to work these 4 together. Toward the end, you'll do much more than I. And then your classwork will really make sure that you understand this concept. On number 2, it says how many particles of sodium sulfate are equivalent to 359 grams of sodium sulfate. So we're going to start with our given. What's our given? 359 grams of sodium sulfate. So we have 359 grams of sodium sulfate. And again, formula writing, critical. And we're going to want to convert to particles of sodium sulfate. Moles is neither given nor asked for. Is it a one-step problem? No, it's got to be more than one step. And so I'm going to turn my paper sideways because otherwise I won't be able to fit. You might, because you don't have to write as big as I do. So what I'm going to look at then is I'm going to set my problem up. I've got 359 grams of sodium sulfate, and in 2 steps I am going to get to particles of sodium sulfate. Now what do I need to do? If I've got grams here, what must go in the denominator of this first fraction? Grams. And if I have grams in one part of the fraction, what goes in the other part? 1 mole of it. And where do I get this grams from? Periodic table. I've got 2 sodium, 1 sulfur, and 4 oxygen. So I've got 2 times sodium off the periodic table, 1 times sulfur, and 4 times oxygen. So I can get the formula mass here. And I do want to point something out to you because sometimes the kids are very confused with the units. the formula mass is in grams per mole. The 1 mole is here, so in this part of the fraction I only have grams. Watch your units, make sure they cancel properly. So I have 142.042, and this cancels with this. So you can't put moles here and grams per mole here. Grams per mole splits into moles here and grams here. Now I'm in moles and I want to get to particles. So if I have 1 mole here, what goes here? I need this unit to cancel out, so what goes here? 1 mole of it. And for particles, what number always goes with particles, atoms, or molecules? Avogadro's constant. And it's particles now instead of atoms because you've got an ionic compound. Multiply the numerators, divide by the denominator. And you have 1.52 times 10 to the 24th particles. And again, this is exactly like we did yesterday, except you have a compound instead of an element. Questions on number 2? All right, number 3 is very similar also. On number 3, it says, how many particles of sodium, no, we just did that one, silly. On number 3, it says, what mass of aluminum chlorate, so that's what we're looking for because no number is given, is equivalent to 1.25 times 10 to the 24th particles of aluminum chlorate. So what's my given? You got it. So we're going to start with the given, which is 1.25 times 10 to the 24th particles of aluminum chlorate. And again, you must be able to formula write with ease. And you want to get to mass. Now, moles is neither given nor asked for, so it's got to be more than one step. And we want to get to the mass of aluminum chlorate. What should I do? Absolutely. Avogadro's number in the denominator here, why? Because you're going to cancel that unit out. And what always goes in the other position? 1 mole of it. Now you're at moles and you want to get to mass. So what are we going to put in the denominator of this second fraction? Mole. And in the numerator we will place mass. And where do we get that from? Periodic table. And we've got to get that. How many aluminum do we have? We have 1 aluminum. How many chlorine? 3 is correct. And how many oxygen? You got it. Make sure you multiply. It's a distributive property similar to math. And so the formula mass for aluminum chlorate is 277.332 grams per mole. And again, you're splitting that unit, if you will, here. So you have grams in one part of the fraction, mole in the other part. So you have 277.332. Multiply the numerators. Divide by the denominator. And you have 576 grams. Yep. So the way I express it here is grams per mole, but I'm taking 1 mole of the substance and placing it here. Placing it here. And so the grams goes in the other part of the fraction. What I see kids do a lot is they'll do grams per mole here and then moles here, and that's incorrect. So it's grams per mole, but you're splitting it over the fraction. So grams in one part, moles in the other. All right? Pretty straightforward. I'll let you try number 4. And then in your classwork, you should have worked through number 12, and now you can work through number 16. So for tomorrow, I'd like to see numbers 1 through 16 done, and you can spend some time today doing that. 13 through 16 is exactly like what we did today. You have to understand formula mass and molecular mass to do percent composition. So try and do number 4. I'll write number 4 out for you, and this is the classwork that should be completed through tomorrow. Again, for today's lesson, 13 through 16. So number 4 is on the screen. Give it a shot. I think you'll find it relatively easy. You already have the molecular mass for glucose right here, so you can use it. And you can see if you can set 4 up on your own. If you get it right, you're in great shape. Did you get what I got? 1.19 times 10 to the 24th molecules? Yep, great. One other thing I just want to point out, because I want to make sure you get full credit on your quiz. Make sure in your fractions you always have 3 pieces in each part: a number, a unit, a substance, a number, a unit, a substance, a number, a unit, a substance, a number, a unit, a substance. And then you won't lose any credit on your setup. There's points for the setup, there's points for calculating correctly, etc. So there's a lot of partial credit to be had. But especially in this class, I fully expect that you will get the answer correct, showing all of your work for very high scores on this quiz. So what you should feel very comfortable with is doing basic conversions, either from mole to mass, mass to mole, atoms to moles, moles to atoms, particles to moles, etc., from mass to particles, molecules to mass. And you can now do this not only for, boy oh boy is that crooked, not only for elements, but after today you can also do it for compounds, both ionic and covalent. And kids usually find this to be the most challenging piece of the puzzle for the chapter. So if you can do this, I think you're in great shape.